All right, so today I want to start off the next section, which will be discussing some advanced topics in Green's functions, in the theory of Green's functions and propagators. For those of you, I guess it's just Sebastian and Nitin that are doing the string theory course, this will sound a little familiar. There's quite a bit of overlap in at least some of the techniques that we'll be using now. And what we're using in the topics in string theory. So if you're doing both, keep an eye out for concepts that overlap. Any logistical questions while we're waiting for this to set up? Okay, it sounds like no is the answer to that. So I want to, in this section, what we want to do is extend our thinking about the Green's functions that we will have encountered way back in, sorry, just before I go on, Nitin's just asked me to remind everybody to submit assignment number 2, please. Send an email to Nitin to submit your work, please. Assignment number 3 will be coming out at the end of this week, so please make sure that you hand in assignment number 2. Well, either the end of this week or sometime early next week. All right, so today I want to start just thinking again about something that you should be familiar with from your second year work already, which is the idea of Green's functions, or solutions of differential equations using Green's functions. Now, if I'm very honest, until I actually started my PhD even, I don't think I fully appreciated, even though I'd done maybe 2 courses in differential equations, one in ordinary differential equations and 3 actually, one in partial differential equations and then one in boundary value problems. I don't think I fully appreciated what Green's functions were, nor how powerful they were, until I actually had to use them in a research problem. When you actually kind of learn to grasp their significance. And I must be honest, this appreciation has just been growing. And as I prepare my notes for this course, I get to revisit these ideas and think again about how they impact some of the work that I do. So in particular, my direction that I'll take in investigating the idea of Green's functions, again, is somewhat unusual from what you may have encountered. So we're going to be focusing on operators and operator methods. So we're going to be thinking of differential equations as eigenvalue problems with some differential operator, just like we've been doing in the last couple of lectures in the first part of the course. Only here, I want to try and use Green's function methods to solve these eigenvalue problems. So, we're not going to be too concerned with this differential equation or that differential equation because they're all just special cases of a general principle that we're trying to establish here. And the general principle is one of using operator methods and how the idea of Green's functions fit into this scheme of operator methods. So to begin, I want to just remind us a little bit about Green's functions. So what we're going to do is just make some preliminary observations about Green's functions and how they fit into eigenvalue problems. And then I'll solve a particular differential equation, it will be a particularly simple differential equation, using this idea of essentially what we're going to be doing is finding an eigenfunction expansion of Green's functions. And you'll see that this is related to the standard idea of Green's functions that you will have encountered when first solving differential equations, or maybe second solving differential equations. And then I want to introduce the idea of causal Green's functions. And the name comes from the physics literature where causal Green's functions, if you remember from your second year course in boundary value problems, for example, the Green's function is in some sense the inherent response of a system. So if I give a system some kick and I want to know how it responds, the Green's function encodes that instantaneous kick to the system, right? And so then we'll come back to looking at the idea of the integral representations of the causal Green's function, which encodes a causal relation between cause and effect in various physical systems. Of course, the physical system that I'm going to be interested in is going to be the harmonic oscillator. And then today, Thursday, I should say that I'm not going to be able to do a live lecture on Thursday, but what I will do is record the lecture and upload it. And on Thursday, I'm going to start a section which will take us maybe 2 lectures, which is a real example of the kind of formal methods that I'll be describing in this lecture, applied to a really interesting problem called the Caldera-Leggett model of friction. The question is, how does friction appear out of some microscopic quantum system? And so we'll use the methods of Green's functions to understand the Caldera-Leggett model of friction. Okay, any questions? Let me just quickly check by way of raising hands. Is there anybody who has not encountered Green's functions before? Good. Wait, let me just check that. All right. So everybody has seen Green's functions in some form or the other before, and I'm going to take it for granted that you know that the Green's function is the inverse of the differential operator that you typically would encounter, okay? So let's start off then by thinking about an eigenfunction equation, okay? So consider the following eigenvalue problem. Which looks like this. We're going to have some differential operator L acting on some set of eigenfunctions. Let's call them psi n. And this is going to be lambda n psi n. Of course, these are the eigenfunctions. Psi n, this is the eigenvalue. And this is the differential operator in question. There are, of course, some caveats that we would need to include in what kind of differential operator, et cetera, et cetera. At this point, we don't really care too much about that, right? We're going to assume that all the necessary caveats that need to be met are in fact met. My claim here is that the Green's function for this problem, for this differential equation, and I'll tell you what I mean by this just now, the Green's function for this differential operator L can be expanded in terms of the eigenfunctions psi n and the eigenvalue is lambda n. So my claim, the Green's function which let's call it G. And let's, for argument's sake, say that we're dealing with a one-dimensional system. So L is a function of X and the psi n's are a function of X, etc. So my Green's function is going to be a function of, let's say, X and psi. And I'm claiming that it can be expanded in terms of the eigenfunctions psi n and the eigenvalues lambda n as follows. G of X psi is the sum over n of psi n of X psi n complex conjugate of psi over lambda n, provided that none of the eigenvalues of L vanish. So as long as none of the lambda n's are equal to 0. If this is the case, my claim is that this here is really an eigenfunction expansion of the Green's function. Now, I made a claim. I should really justify this claim to you. Otherwise, I should just shut up. So let's show that this is indeed a Green's function for the operator L. What do I need to show? What do I need to do in order to show that this Green's function is a Green's function for the operator L? Anyone? Take a guess. Otherwise, I'm going to randomly ask.
Could you repeat the question, please?
What does it take to show that that expansion, that G of X and psi that I wrote down, is a Green's function for the operator Lx? What do I need to do to show you that? How would I convince you?
That if we take, wouldn't it be that if we take G and act it on L, but then L is also a differential operator?
Who's speaking?
Eric, sorry.
Eric, yes. Say again?
I was thinking, wouldn't it be that we would have to take G and act it on L or vice versa? Maybe expect that they'd give us 0, but then again, L is a differential operator, and so...
Okay. Yeah. Cabello?
Yeah.
Apply L to G and you should get a delta function.
Great. So you both were correct, and Cabello was more correct. G, remember, is an inverse of L. So to show that you're going to get G as the inverse of L, if you act on G with L, you should get the identity. Of course, because we're dealing with continuous differential operators, as you've noted, Eric, the identity is not a Kronecker delta. It's in fact a Dirac delta, as Cabello pointed out. So that's what I need to do, right? In order to show this, I need to act with L on G and hope that I get the Dirac delta. So let's see this. To show this, note the following. L, and I'm going to denote it by L subscript X, meaning that it's a differential operator, but it's going to be a differential operator just in the X variable, okay? So I'm only acting on any X dependence in G. So L, G, which is a function of X and Xi. That's why I'm taking pains to denote the X dependence on L, is Lx acting on this sum. So sum over n, psi n of X, psi n of Xi, complex conjugated, all divided by lambda n. The L acts only on psi of X. That's the only X dependent. So I can take this into the summation. That's the sum over n. Lx acting on psi n of X and nothing else. So there's this guy floating around. And then I have to divide all of this by the lambda n's. And this is equal to the sum over n of lambda n psi n, because psi n is of course an eigenfunction of Lx, psi n conjugate of Xi, all of that divided by lambda n. The lambda n's of course cancel. And so what we're left with is the sum over n of psi n of X, psi n conjugate of Xi. But of course, we're making an assumption on L and its eigenfunctions that ensures that this guy here on the right-hand side is a complete basis. And if it's a complete basis, then if the psi n's, the set of eigenfunctions, form a complete orthonormal basis, then if I sum psi n's conjugate, I'm going to get nothing but the Dirac delta function of X minus psi. Hence, G, as represented in this sum here, G as represented in this sum is in fact a Green's function corresponding to the differential operator L. Let's do an example to illustrate this. I want to make a note here actually. So this is because the set of psi n's form a complete basis. So let's do an example. And I'm going to start off by doing a very trivial example, and this is the example of essentially in physics what we would call a free particle. Kiniso.
So can I please ask on what page are we on the book? Because I'm just trying to check. I can't find it.
I'm sorry, what?
On what page are we on the book?
Gosh, I'm not sure. I'll have to I'm gonna I have to pull it up and look for it. I can tell you a little later in the I'll send you an email for where we are in the book, but I don't have the book on me right now, and I'll have to locate it and open it up to the page.
Okay, thanks.
Okay, so let's do an example, and the example I want to do is a very simple case of L just being a straight up second order differential operator. So let's consider the following. So I'll take Lx or L to be minus dx squared. So that's just basically minus d2 by dx squared, right? That's what I'm going to mean. And in fact, I might as well just use this the latter notation. And I want to consider this on a particular domain. And the domain is going to be the set. So the domain of L is going to be the set of functions y and Ly in the set of square integrable functions on the interval from 0 to 1. So this is a set of square integrable functions on the interval, on the x interval from 0 to 1, such that y of 0 and y of 1 both vanish. So those define the boundary conditions for me. And this defines the whole eigenvalue problem. Sorry, just give me a second. Let me preemptively apologize for barking dogs. So that's it. I have a differential operator. I have a differential equation. The differential equation will be minus d2 by dx squared on some function psi of x equal to lambda psi of x. Okay, and I want to solve this differential equation, and I want to figure out what its eigenfunctions are and what the eigenvalues are. So subject to these boundary conditions that y of 0 vanish and y of 1 vanish, there is one set of functions that will do it for me. This is a second order differential operator. So I'm asking for functions whose second derivative are the functions themselves, except with this minus sign here. So can you think of a function whose second derivative is minus itself?
E to the minus x.
And that satisfies those boundary conditions.
Sines or cosines?
Sine of x.
Sine.
Sine, good. Very good. So eigenfunctions of L are the functions psi n of x equal to sine n pi x, right? Sine of n pi x will satisfy the differential equation. And in fact, if I want to figure out what the eigenvalues are, I'll take this sine of x and I'll plug it into the differential equation and see what happens. So if I do that, we will find that minus d2 by dx squared acting on these psi n of x. Every time I differentiate, I pull out an n pi and I differentiate twice, so I get a minus sign, which cancels off the minus sign in the front of this. So effectively, I'm going to get just n squared pi squared times sine of n pi x, which implies that the eigenvalues for this eigenvalue problem, lambda n, is just n squared pi squared. Great, so now we know what the eigenfunctions are, we know what the eigenvalues are, and we can immediately read off that the Green's function from my previous claim, x and psi is just the sum from n equals 1 through to infinity of 2 over n squared pi squared sine n pi x sine n pi psi. And as an exercise for you, it's a very quick exercise, but do it nevertheless. Where does this factor of 2 come from? So explain this. But that's it. That's the Green's function for this problem. Now, for those of you who remember your Green's function introduction back in the day, you would know that this is just a free particle problem with a particular set of Dirichlet boundary conditions. And so you probably already know that there is indeed a Green's function, which probably didn't look like this one. However, in the intervening years, you probably learned about Fourier series, and this is nothing but the Fourier series expansion This is the Fourier expansion of g of x psi equal to x times 1 minus psi if x is less than psi, or psi times 1 minus x if x is greater than psi. So this, this is what you would have seen in the past, that if you solve this differential equation for the Green's function in the standard way that you would solve differential equations for Green's function, you would have gotten this expression for the Green's function. And it satisfies the same boundary condition that the differential equation satisfies. And you can check that explicitly. And it tells you how to solve the differential equation, right? Our Fourier series, sorry, our eigenfunction expansion of our eigenfunction expansion of the Green's function is identical to what you would have found in the past, except that is the Fourier series representation of the same function that you would have found. Any questions? So I see that Nitin has put the page number in the chat, if you want to look it up there. Okay. Now, if there are no questions, let me point out something which I hope you would have seen, which is what I did here. Notice that I am not summing over the specific eigenvalue lambda naught, because that eigenvalue vanishes. And so the question that one would necessarily ask, because I had put this caveat in the previous slide, which is that this expansion holds whenever none of the lambdas vanish. So what happens if one or more of the eigenvalues are 0? Well, in this case, we simply define a modified Green's function by dropping the 0 modes in the expansion. So let's make a note of that. If one or more of the eigenfunctions of the eigenvalues vanish, So if one or more of the lambda n's equals 0, we use instead the modified Green's function, g of x. In fact, that's g modified of x psi equal to the sum. Now I'm going to sum over all n such that lambda n is not equal to 0. Again, psi n of x, psi n conjugate of psi lambda n. Okay, so this will be the modified version that accounts for any vanishing eigenvalues. So in this case, if I know that some of the eigenvalues vanish, this modified expression will encode a series expansion for the Green's function.
Okay, I found this on the web for Hay series expansion for the Green's fraction.
Sorry, I'm not sure if you heard that, but that was Siri getting involved in this lecture. Where are we? Okay. All right. So now I would like to let's give you an exercise, and for this exercise, I want you to do the following. I would like you to show two things. The first thing is that, in fact, the first thing is that Lx acting on the modified Green's function is also delta of x minus psi, but the contribution of subtracting off the zero modes from this contributes an additional term, which is the sum over lambda n equal to 0. So just summing over the zero modes now, psi n of x, psi n conjugate of psi. Okay, so that's what happens if I act on this modified Green's function with the differential operator. The second thing I'd like you to show is that G modified is also Hermitian and orthogonal to all of the zero modes of Lx. So show that this guy is Hermitian. With respect to the standard inner product on this space of functions, and orthogonal, again, with respect to the same inner product to all of the zero modes of Lx. The zero modes of Lx are the set of all psi's such that that have zero eigenvalue. Okay, so up until now, you've probably thought of Green's functions as some function of real values x, because you probably worked with differential equations that were just differential equations in x, or partial differential equations in x and y, or something like that. But all of the independent variables and all of the functional dependents were in terms of real valued things, x typically. But as we've learned in the last part of this course, where we took differential equations that we would normally study on the real line or the real plane or real three space, and we continued them into complex variables. We, of course, just did this for ordinary differential equations. So we started with the real line and we continued it to the complex plane. And we saw that when you do that, there's an immense power that comes from being able to apply the theory of complex variables to solve these differential equations. Okay, and in particular, analyticity of the differential equations plays a big role, and the fact that the coefficient functions are now functions of a complex variable allowed us to even classify these differential equations, classify the solutions of the differential equations according to the singularity structure. Well, it turns out that something very similar happens in this case too. And we can really fully appreciate the power of Green's functions by continuing in the arguments into the complex plane. So to this end, I want to consider the following Green's function. And this is called a causal Green's function. And I'll explain why just now. So now let's consider the causal Green's function. Which I'm going to call g, and g is going to be a function of t minus tau. And this guy is equal to 0 whenever t is less than tau. So remember that the Green's function measures the response of the system. So what we're saying is that this guy is a causal Green's function because nothing happens in the system until there's an initial kick given to the system at some time t equal to tau. So at time t equal to tau, I stop my stopwatch, give the system a kick at the same time, and watch what happens. And this Green's function measures precisely that. So if I then consider the Green's function for all times, nothing happens before time t equal to tau. At times t equal to tau, there's an initial kick given to the system, and the Green's function tells me how the system responds to that kick. So this is causal because, comment. This is causal because nothing happens until, this is the response to an initial kick to the system at t equal to tau, before which nothing happens. Okay, so that's why we call it the causal Green's function. So let's take the Fourier transform of G and see what we can learn from it. So taking the Fourier transform, gives us an integral representation which looks like, let's call it G tilde of omega, which is equal to, with some normalization, the integral from 0 to infinity of e to the I omega t G of t dt. Of course, what I mean by this is really the limit as some regulator t goes to infinity of the integral from 0 to t of e to the I omega t G of t dt. Okay, so that's how I define the integral and make sure that it converges. And of course, the integral will converge whenever omega is a real number, but it converges also for complex numbers omega, and it converges even better when the imaginary part of omega is also positive. So this integral will converge the integral converges if omega is real, but also if omega is complex with the real part of omega greater than 0. And it converges even better if the imaginary part of omega is also positive. So in other words, this quantity here, G tilde of omega, is well behaved. In fact, it's also analytic everywhere on the upper half omega plane. So this is analytic everywhere on the upper half plane of complex omegas. Okay. So let's do an example to illustrate. Any questions, by the way? Okay, so a good example when everyone's thinking about these kinds of problems is the harmonic oscillator. So in this case, I want to consider the harmonic oscillator, but I actually want to consider a variant of the harmonic oscillator, which is the damped harmonic oscillator. So the damped harmonic oscillator is just like the harmonic oscillator, except instead of an x double dot proportional to minus x term, there's an x double dot term, there's an x dot term, which is the damping term, which takes away energy from that harmonic oscillator. And then there's the minus x squared, minus x term, right, which is the harmonic term. And if you go to my notes, there's a solution in the section on Green's functions, the initial section on Green's functions, there's a solution of the damped harmonic oscillator in terms of Green's function. So I'm just going to write down what this is for now, and you can revise how to get there from my notes. Okay, so the Green's function for the damped harmonic oscillator with damping coefficient gamma and natural frequency capital omega is given by the following. G of, in fact, it's G of T is equal to 1 over omega times e to the minus gamma t times sine of omega t if t is greater than 0, and it is 0 for t less than 0. So notice that this is a causal Green's function. Before time t equals 0, I haven't done anything to the system, so the response of the system is nothing, so 0. After t equals 0, I give the system a kick and I watch what happens. And because this is a damped harmonic oscillator, the kick drives some oscillations. But unlike the oscillator, the standard oscillator, those oscillations are modulated. So it damps out. So depending on how big gamma is, this could either damp out really fast, or it could take a long time to damp out, or there's some critical damping in which it goes to 0 fairly quickly. Okay? And that's modulated by this exponential factor here. So this is the modulating factor. The natural frequency of the oscillator is given by this capital omega. So this is the natural frequency. This is the damping coefficient. And the exponential term captures the effect of the damping, right? So the oscillations die out exponentially. I really wanted to talk about not this causal Green's function, but its Fourier transform. So the corresponding Fourier transform, G tilde of omega, you can calculate, is 1 over omega squared minus little omega plus I gamma squared. And you can see that this quantity is always finite on the upper half plane, but there are in fact poles at omega equal to minus I gamma plus or minus capital omega in the lower half plane. And in fact, the only way a causal Green's function can have a pole in the upper half plane is if G itself has an exponentially growing factor, which makes it unstable to perturbations. So for example, if there's some driving in the system, right? So that's when I would expect poles in the upper half plane. And we'll come to that in a little bit as well. So notice here that G tilde is always finite in the upper half omega plane, but has poles at omega equal to minus I gamma plus or minus capital omega, where the denominator goes to 0 and G tilde will blow up. And all of these poles are in the lower half plane. Okay. Very good. If I invert this Fourier transform, I will get the following integral representation. So this inverting this gives the integral representation for the Green's function of g of t equal to the integral from, minus infinity to infinity d omega over 2 pi. Again, this is some normalization I'm choosing. Some people use 1 over root 2 pi, some people use 1 over 2 pi, some people use 1. Just be careful about your convention, but as long as you're consistent, it's fine. I omega t omega squared minus omega plus I gamma squared, which is equal to the Heaviside step function theta of t times 1 over omega when I carry out this integral times e to the minus gamma t sine of omega t, as we would expect. And the Heaviside step function builds in for us the fact that, so this is the step function, which builds in for us the fact that if t is greater than 0, it's 1. If t is less than 0, it's 0. Okay. This integral in inverting the Fourier transform is, of course, a complex integral because of this e to the minus I omega t factor. And so a good exercise for you would be to show this using some appropriate contour on the complex plane. And I'm going to leave that as an exercise for you, and we will pick up again. So live lectures next week. I will record a lecture on Thursday and upload it to the Vula page so you can see what we'll do. But just for a heads up, we're going to be studying the Caldera-Leggett model of friction. So I want you to show this. Explicitly. Any questions?
Sorry, I kind of get lost in noting down everything you're saying. I didn't quite understand why we're inverting. Could you just please brush that up again? So the part where
why we're doing the inversion?
Yeah. Inverting this gives the integral.
It's a sanity check on whether we get the right answer, whether we're getting the right answer. So I started off with g of t. I did the Fourier transform. I'm now inverting it. And you can see exactly how the causality appears out of this. In other words, the theta of t tells me, which is either 0 for t less than 0 or 1 for t greater than 0. That tells me precisely when the kick kicks in at t equals 0. Now, of course, I wrote down the original g of t, knowing what it should have been. But I could have just as well started with the damped harmonic oscillator equation, took a Fourier transform of that damped harmonic oscillator equation, gone to omega space, it would become an algebraic equation, solve for g tilde of omega. I will have gotten precisely what I wrote down for you, and then did the inversion, and you would have come to the same conclusion. Make sense?
Okay, yes, thanks.
Sure. Any other questions?